everybody. I'm today talking about the HICANN wafer system, which is the neuromorphic hardware developed in Heidelberg. And to start with, I want to introduce HICANN. This is the HICANN chip. It's a high input count analog neural network chip. And this is the basic unit of the HICANN wafer system. And it's built up of synapses. We can't look at this as some memory and 256 neurons in total 512 neurons. And the first important thing to say is these neurons are analog. And I felt like when talking, like not everybody really knows what it means that the neurons are analog. It means there is an electrical circuit that actually represents physically that neuron. So there is no differential equation which is solved in the simulation. There's a capacitance and there's some current flowing, and this capacitance, for example, is the membrane potential. So this analog computation has some consequences. First of all, there's significant variation. Like if you repeat one experiment, it's not going to be the exact same result. Like maybe yesterday it was 1 degree hotter or colder, and the resistance was a little bit different, so the exact result will not happen. And then there's variability across neurons, of course. If you have two different circuits, they're not exactly the same. And the second thing is, you can't just push pause and continue your simulation data or look at the data and then continue. If you push pause, the circuit is still going to do what the circuit does. There's a current flowing, the capacity is changing, so this is analog computation. So the second property is that we have a really high neuron input count, so every neuron can have one neuron can have up to 10,000 incoming synapses. And that's why there's so much space for the synapse and not so much for the neuron. And but since we have only 512 neurons on one chip, there is a wafer system. So this small plate down here is a wafer, and there are 384 of these HICANNs, and this results in about 200,000 neurons and 14 million synapses per wafer. And well, currently the goal is to put 20 of these wafers in a single rack, so we have 4 million neurons and close to a billion synapses possible. Yeah. And one more very important property is that the hardware is accelerated with a factor of 10,000. That means if you want to emulate an experiment, 10,000 seconds in biological time, it's going to take 1 second in the hardware. So now just an idea of what kind of networks we emulated so far in the HICANN system. So these are rather simple networks because it's still in development. For example, the feed-forward network, very basic one. The neurons of one population are just exhibiting the neurons of the next population, and therefore a signal from spike source is just propagated to the populations. And that's something you can do on the HICANN already, but it's possible, and the simulation and the emulation get similar results. What I've done in my specialty is working with recurrent networks, so you just have two populations inhibiting each other directly, getting different stimulus from sources, and so you can look at competitive dynamics a little bit by changing the stimulus. And that's also possible, that's working. And then there are closed loop experiments where you calculate some part on the hardware and some part of the hardware on a conventional von Neumann computer. So for example, this is a task where you just follow a point in your receptor field, and in the software it says the point is, for example, left, it has this velocity, and this is some input that is coming to a neural network, and that tells you, okay, it has this velocity in this position, and the network calculates the response. That means I have to move my head to the left, for example. And then your response is going back to the software, to the computer, to the von Neumann computer, and there the new position of the point is calculated. And you can do this like running for 15 minutes, whatever it is, which is kind of following the point. Yeah. So, to sum it up, because it's so less time, the experimental challenges here are minimizing neuron-to-neuron and child-to-child variations. We work with the neuromorphic hardware, and this is done by calibration, first of all. This is one of the things in development, and increasing population size. For example, if we go back to this recurrent network down here, in simulation would be enough to just take 2 neurons in populations, but like if you're on the hardware, you can take populations, so in the mean, the population is behaving similar. So then some words to the time. Like currently, if you're doing the experiment, the bottleneck is the calibration time, which is about 30 seconds. If you think about acceleration, like a normal experiment, we're going to be really fast. So The acceleration is only advantage.
5 minutes.
Yeah, I'm almost done. So the acceleration is only advantage for long experiments. So, well, go ahead.
Keep going, keep going. You'll know when to stop because I will sign close to you, right?
Alright. Okay, so just outlook. What's interesting is as soon as you start having larger networks and everything, like we will be able to do long-term learning, for example. We can investigate networks which are on a longer time scale and just have less time to emulate them. And the thing is, with increasing the network, the emulation time doesn't increase, since it's all analog computation. And you can, for example, look at structured plasticity, so the synaptic connectivity changes over time while the network is doing an experiment. And what's also interesting is iterative tasks where you have, like, for example, on a simulation, you have a simulation and it will take 1 day, and then you say, oh, I maybe should change this parameter a little bit, and then you do another day. Well, on the compute, like, there's a goal that you can click and it's done, and you can just change the parameter again. So that's close to the experiment and network experiment. Okay? I think that's already it. One thing. No, it's not.